All right, well, let's get started here. This is question number 3 from the 2014 AB International Exam. As we can see, it's calculator inactive. So it says let f of x equal e to the 2x. Let R be the region in the first quadrant bounded by the graph of y equals f of x and the vertical line x equals 1 as shown above. So the graph is the graph of f of x equals e to the 2x. This vertical line is equal to x equals 1. Since we want to stay in the first quadrant, our other bounds are x equals 0 and y equals 0. Part A asks us to write an equation for the line tangent to the graph of f at x equals 1. Well, what I know is that if I'm going to do this, I need the point on the curve and I need the slope. The point is going to be the point at x equals 1, and we know that the coordinates there are 1 comma e squared. The slope, what we need to find is f prime at 1, the derivative of f at x equals 1. So first we find f prime of x. Well, f of x is e to the 2x, so the derivative is e to the 2x times 2, or even better, 2e to the 2x. The derivative evaluated at 1 is 2e to the 2 times 1, or 2e squared. That's the slope. We have the point. The equation for the tangent line then is going to be L of x equals 2e squared times x minus 1 plus e squared. That's it. That's all that you needed to do in part 1. You were awarded 1 point for finding the correct slope, 1 point for writing the equation of the tangent line, no need to simplify, for a grand total of 2 points. And this is the kind of question that I would expect most students are able to correctly answer without too much difficulty. Let's look at part B. In part B, the question now is, or the statement now says, find the area of region R. Well, let's do that. To find the area of region R, I'm looking for this area here. I can find the area in a couple of different ways, but probably the most natural way to find the area is to look at our representative slices. I'm going to do my slices so that they are perpendicular to the x-axis. In order to find the area, I look at the height of each of these rectangles. Well, the height is just the distance from the x-axis up to the curve, so the height is f of x. The width is going to be dx. So for part B, the area is just going to be our traditional setup of the integral of f of x with respect to x, starting at x equals 0 and continuing until x equals 1. Now, unlike a graphing calculator problem, we're going to have to do this problem by hand, so let's start replacing everything. F of x is e to the 2x. I need to evaluate this definite integral, which involves integrating e to the 2x. The integral of e to the 2x is going to be 1/2 e to the 2x. We then evaluate from 0 to 1. To evaluate, we evaluated the top limit first, 1/2 e squared, minus evaluate at the bottom limit, 1/2 e to the 0. You can stop here if you'd like to, or you can simplify further. 1/2 e squared, there's not really much we can do there, but e to the 0 is 1, so 1/2 of 1 is just going to be 1/2. In terms of how points were awarded, you got 1 point for setting up the initial integral, either this way or this way, where we just say f of x. 1 point for finding the antiderivative, that's the 1/2 e to the 2x. And then 1 point for the plug-in right here, even if you don't simplify, for a grand total of 3 points. Again, I would expect this to be a relatively high-scoring question for most students. These are exactly the skills that we've been working on. So now let's look at part C. Let me move the paper around a little bit here. In part C, we're told that region R now forms the base of a solid whose cross-sections perpendicular to the y-axis are squares. Okay, let's kind of hang on that for a little bit. We can come back to that. Write but do not evaluate an expression involving one or more integrals that gives the volume of this region. So I'm going to redraw this shape a little bit just because I've already marked up the first one. So my x and my y axes, here's the curve, here's the vertical line, x equals 1. And we are told that region R is the base of a solid. And when we take cross-sections perpendicular, let me make sure I'm reading this correctly, perpendicular to the y-axis. Well, here's the y-axis. Perpendicular to the y-axis means that we're going to be going this way. My slices now are sliced this way, which means that we're looking at a dy integral. My top function is f of x equals e to the 2x. We're bounded at x equals 1, x equals 0, and y equals 0. Now, part of what's going to make this a little bit trickier is that we are looking at a dy integral, so whatever we do, everything is going to be in terms of y. Furthermore, we know that the slices are going to be squares. So let me draw a square here just for a second. Here is my square. The cross sections are taken so that this guy here corresponds to these slices over here. So whatever this distance is in terms of y, that's going to be equal to the height in terms of y, because we know we have a square. All four sides are congruent, and we have 4 right angles. And I like to think about these squares as having a thickness. The thickness is the dy. Well, to find the volume of a slice, we're going to say that it's the length, whatever this length is here in terms of y, times whatever length this is here in terms of y, times dy. Well, we're going to have to do a little bit of work. We have to figure out what L is in terms of y. Well, let's look at the diagram. If I'm down here and I'm doing my slices, well, all those slices have the exact same length. That length runs from x equals 0 to x equals 1. That's a length of 1 if I am below the y-intercept. The y-intercept here is at 0, 1. However, when my slices are above the y-intercept, then I'm running from the line x equals 1 over to the curve e to the 2x. That means I'm going to have to look at what happens below the intercept, we'll call that part number 1, differently from how we look at the piece above the intercept, that's part number 2. Well, let's see, the volume for part 1, everything is in terms of y, is going to be an integral of L. How long is that from x equals 0 to x equals 1? 1 squared dy. I need to integrate with respect to y, so I need my y values here. We're integrating from the origin, y equals 0, up to the point y equals 0, 1, so that's a y coordinate of 1. The volume for region 2, well, let's see, where do I start region 2? That's going to start here at the point 0, 1, so that's a y value of 1. And we run all the way up until we hit this point 1, e squared. That's going to be y equals e squared. And it's going to be the length squared with respect to y. Okay, we're doing well here. How long is this length? You're going from x equals 1 over to the curve e to the 2x. In order to express this length in terms of y, we're going to have to do a little bit of side work here. Rather than thinking about the curve y equals e to the 2x, we're going to have to write this in terms of y. We can do that by taking the natural log on both sides. Natural log of y equals the natural log of e to the 2x. we're able to bring the 2x down in front, times the natural log of e. Natural log of e is 1. So we get that the natural log of y is equal to 2x. X is 1/2 the natural log of y. That's still not the length of this slice. We're running from x equals 1 over to the curve, and we've rewritten this now as x equals 1/2 natural log of y. How long is that distance? It'll be 1 minus 1/2 the natural log of y, the whole thing squared. This was the volume for region 1. We found that pretty easily. This is the volume for region 2. This is much harder. The total volume, so the last thing that we want to write, is that the volume will be the integral from y equals 0 to y equals 1, 1 squared dy, plus the integral from y equals 1 to y equals e squared, 1 minus 1/2 natural log of y, the whole thing squared, dy. In terms of how points were awarded here, let me find my scoring rubric. The integrand, this expression here, was given 2 points. Having the correct limits was worth 1 point. And then the whole expression together was worth a 4th point. This was a grand total of 4 points. I would definitely recommend coming back and looking at this video one more time. Make sure you're clear with everything that's happening. The fact that the slices were squares, that's rather kind. The fact that they're perpendicular to the y-axis makes it a little bit trickier because now everything's a dy. And then from there, it's just a matter of find the volume for the first region, find the volume for the second region, and pull everything together. I hope you found that helpful.